So, hello everyone. Thanks for coming and joining us. You're in for a fantastic treat, I believe. This is a technology that we have been developing for more than 2 decades, and it's using an integration, the heterogeneous integration of photons and electrons to reduce power. And I'll get into some of the background information on this later, but we started this journey because the US government had a program called, and I believe is going to get revived, called the Joint Strike Fighter. And their goal was a DARPA hard and an Air Force desire to get rid of RF copper cables, which were used for electronic warfare, and replace that with fiber. And like all DARPA hard programs, it was Heilmeier rules that were very, very tough to accomplish because that technology had matured over 4.5 decades, and the aerospace military complex had squeezed every tenth of a dB out of analog communications on RF cables. The good news was, if we did and were successful in solving that problem using fiber, then it was a great waste saving and other benefits, including less vulnerability to EMI and EMP and things like that. So we embarked on that journey, and there were many, many competitors. And at every step, DARPA's requirements stayed the same but got harder and harder because we had to get rid of certain things that were very, very complex. So it was purely the link. You needed a light source, laser, you needed a detector, and you needed a modulator, a simple link. And as like anything, these things had matured for the copper or analog electronics world quite a bit. And so we had to have some fundamental breakthroughs for the laser technology. We had to do something fundamental for the detector and also for the modulator. That's how we came up and solved that problem. And it had to be on a single fiber. We had to demonstrate 16 channels, 8 of analog and 8 of digital, and meet all the requirements that a copper cable was going to do. I mean, this was hard, and we did it. And with that, the technology then became of great interest to NSA, because NSA was reviewing that program, which brought us to this journey, and you're about to hear about how that technology evolved into reducing power and energy consumptions for computers. With that, let me introduce you to one of our partners, and Edmund will give the first part of the presentation. Oak Ridge National Lab and Air Force are our partners, and with that, Edmund, you're sure.
Thank you. And I'll stand up so I can show you some things on the screen as I'm presenting. I need to stay away from this microphone. So, good morning. My name is Edmund Begoli, and I lead Center for AI Security Research at ORNL. My colleague Amir Sadovnik, who's our research lead, is here as well. The reason why I'm here is because at Oak Ridge, part of this presentation is going to talk about this is that we have significant AI resources and building things at a very large scale. Up until recently, the largest supercomputer in the world was at Oak Ridge and all that stuff. But in a security domain, we observed the need to be operating in a different kinds of environments and to be able to fit AI into much, much smaller places, which half of this presentation is going to be about that. And the second half is going to be about specific techniques, what these techniques are and what kind of energy, power, and space savings do you accomplish. And so that kind of connects with the rest of the story in terms of how AI is evolving to the general public in a very different shape. On the other hand, specifically from a security applications in a very targeted domain. So why this topic matters? What you see here on the left is the news about the movement to build gigawatt data center campuses. Okay, these things are coming, and so you know that in Memphis there's already XAI has a very large campus, and they're doubling the capacity. And so we all know about the purchase of the very, very large, the size data centers for the GPUs and power utilization, power, and so on. On the other hand, if you look at, and this is here strictly talking about a purely civilian commercial market, there is an explosion in IoT and embedded devices in microelectronics where they're being placed in every possible piece of electronic we can think about. So in one way, you can see there's this dichotomy. And one is that we are really looking into this gigantic power-hungry AI. On the other hand, we have this market evolving that talks about 30 billions of connected devices by 2027 that range from AirTags and keychains and pins and things that are going to be revealed through OpenAI, new partnerships and all this kinds of stuff. In other words, embedded electronics in everything and everywhere that, of course, we want to make it smart. We want to make it AI-enabled. So again, these two things right now, if you look at them on surface, they really don't connect. The large language model, which we're all proud to say, it's so many trillion parameters and it takes so many hundreds of thousands of GPUs to train. On the other hand, we want to have an AI on an extreme edge. So what I'm going to talk about today is actually what is the technology that enables bridging that gap with a very specific applications in a security space. So first, what I'm going to introduce is TinyML. TinyML is the label for a canonical framework that was developed originally by the scientists from MIT and Harvard. And really, TinyML is the TensorFlow Lite for microcontrollers. So what does that mean? You train and develop a regular machine learning model for sound, speech, image recognition, text interpretation, classification, and so on. And then you run it through a number of processes that make it small and make it efficient and ultimately make it targeted to the specific microcontroller environment. So the key word I want to emphasize here, and this is going to be the kind of topic as you hear today, is that once we start moving in the microcontroller and edge computing environment, we move away from general purpose computing towards specialized. And I'm just going to say this thing a little bit off script, is that what are we right now working in Oak Ridge is actual development of, there's a project called Apache TVM. We are working on development of the kind of cross-platform compilers because right now we are in the same situation where we were, if you look at from a visionary point of view, we're actually just scratching the surface of this work. But if you go back to 90s and then 2000s, what triggered development of Java programming languages that prior to that in C and C++, we were programming for particular platforms. And then Java kind of extended us. And by the way, original Java was developed for a desktop devices for cable networks, is to enable us to work on multiple platforms. However, when you talk about TinyML, we are really talking about taking a general purpose, very potent machine learning model and being able to minimize it and then being able to compile it for a specific microcontroller platforms. And what I'm going to show you today is specifically related to the research we're doing. We have had some real groundbreaking results in this space, and so that's going to be towards a little bit later. So anyway, to summarize, TinyML is a TensorFlow Lite for microcontrollers. State-of-the-art machine learning models that have been squeezed into incredibly small places. One side application to give you something you may be interacting almost every day. When you think about Alexas and other kinds of these assistive devices that can recognize the speech and can recognize some kind of environmental events, they're most likely developed using similar kind of technology or exactly the one. This is going to go now into more technical details. Let me motivate this subject, why this actually matters. When we started working on this a couple of years ago, this was completely esoteric space. I mean, you talk about people, only people from national labs, Google and OpenAI were kind of even familiar what are we talking about. 4 or 5 months ago, DeepSeek has completely changed the game because what DeepSeek has done, they have adopted a few of these techniques which we've been using, which I'm going to describe, to accomplish what broke the market for at least a couple of weeks because they were able to train their models and deploy them in environments where they were reduced in terms of access to GPUs. So that's why I kind of want to tell you that when I was presenting this a year ago, this was mostly for like a high-end technical community. Now when I talk about this, I think that DeepSeek has really brought this to the mainstream in terms of importance of these kinds of reduction techniques. So what they are. Okay, you might not have any background in artificial intelligence at all, machine learning. So I'm going to take a minute to just go through it briefly just to tell you what it is. If you know, the machine learning is ultimately, the state-of-the-art AI is mostly based on deep learning. Deep learning is really about very large neural networks. Very large neural networks can have billions of weights. What these weights are, They're really numbers that represent matrices that are multiplied against or processed against each other. And they're very, very large, and the reason why you need GPUs is because GPUs support parallel processing or parallel matrix multipliers. The techniques we're doing is all about taking these massive deep learning networks and then shrinking them as much as possible to be as small as possible. They're not known to be small. One big thing about deep learning is these are big deep learning networks, big numerical networks. So 3 techniques we use are quantization, pruning, and clustering or weight sharing. What does this mean? Quantization means is taking a number such as 32-bit number and understanding that the most of the weights only use a small portion of that word size, 30-bit size. And then understanding that if the majority of the weights in the network really don't need to be 32-bit wide, shrink them down to be 8-bit. And by that, you already get a significant reduction in size. The pruning technique is following. So this goes back into the in-depth understanding of deep learning. But when the network settles after the training, it's understood, and this is when you talk about explainable, interpretable AI, it's really understanding which weights contribute to particular decision processes that come out of the network. Many of the weights are never used. And so pruning techniques means strictly going and removing them completely, understanding that they never get activated in any calculations that have any meaningful outcome to the result, and just throwing away. So that's another reduction technique. And then finally, clustering or weight sharing is really interesting. You also, when you study how neural networks, when these weights get multiplied against each other and produce the end result, you realize that maybe 6 or 7 weights all yield the same numerical result. Even if you multiply 7 numbers, you will still give the same value at the end. So in other words, what you do is rather than keeping those 7 numbers, you kind of drop them all and you just have one representing. And that goes back to clustering and weight sharing, understanding that these groups of weights all contribute to the same results and then ultimately have them represented by a single weight. Results, as I'm going to show you, are dramatic. They're significant. This is what enables us this next generation of computing of this, I'll call this extreme edge AI. So here's the results. So if you see on the top, the full precision network is about 6,000 kilobytes, okay? There's the number of techniques here that we've been using, quantization and pruning and various different forms of clustering and so on. And then finally, when we combine, our network size drops into the tens of kilobytes. So from 6,000, so the 16 times reduction. This is what enables us now to say we don't need all these massive GPUs to squeeze them into the small drone or to squeeze them into the robot or something like that. We can take all these state-of-the-art networks and actually squeeze them into very, very small places because they fit into tens of kilobytes. And that was the kind of breakthrough that is still happening. We're still very actively working in this research, and so I'm presenting here, of course, understand this is not an AI conference in terms of research conference, this is a consumer conference, but I want to tell you that this is the breakthrough that is kind of happening on the fly, this specific application here of speech recognition. And then what you see here is we combine these 3, pruning, clustering, and quantization techniques with also compressions themselves. Another path that we are exploring significantly is that one is to take canonical TinyML, in other words, TensorFlow Lite for microcontrollers. Another one is to look into Rust and other compilers that can enable us to produce, and 2 keywords which you're going to hear through this conversation is the small and safe. And so this is the work that we're observing right now. You can see some of the bite-size reductions, using various different languages, and you can see that with Rust we were able to accomplish 72% reduction and so on, and on the ARM 32-bit platform, all the way to 98%. For the sake of time, I'm going to have to speed up a little bit and just. So I'm going to stop here, and I'm going to ask you. So just to summarize this. This is work in progress. What I'm presenting you is the bleeding. I keep saying this with my colleagues in the lab. It's not even bleeding edge. I call this abyss. People throw at us problems such as like the state of the art is 100 kilobytes. Can you get smaller? Well, we use binary neural network and we're able to get into tens of kilobytes. And we're still able to maintain performance drop from like 93.5% to 92.5% F1 score and so on. So in other words, it's really, really good. It's a bleeding edge. I don't want to take any more time unless somebody has a super quick question that I can answer, and I'll let my colleagues connect it to the rest of the story with microelectronics.
We will have questions and answers later on. So.
Okay.
All right, good. Let's go with the flow. So thanks, Edmund, and let me introduce you to Brett, who's to the next piece of the presentation, also from Oak Ridge Land. Go, Brett.
I'm going to stand up as well. Let's see. Yeah, so I actually think my talk's going to be very complimentary to Edmund. And then I'm going to try to transition into our optoelectronics work with APIC. All right, everybody, I'm Brett Witherspoon. I'm a R&D staff at ORNL, Oak Ridge National Lab. I specialize in low power, highly reliable, small form factor embedded hardware and software systems. So today, two things I want to share today. I want to kind of talk about some of our, we've been, for a long time, had microelectronics capabilities at ORNL, but is particularly in the context of AI and national security, we've really been building up these capabilities in the past 2 years. So the best way I know how to describe that is show you some of the projects we've been working on, either completed or currently working on. And then the other thing I want to do is highlight the really recent project. I just started a week or two ago, right, on this project, but it's an optoelectronics project we're really excited about, and that's our collaboration with APIC. And Bob and Raj are going to have presentations after me to give you some more of the details, but I have a little transition slide at the end. So let me start with, okay, so I have more slides than I probably have time, so I'm going to go through quickly. But I think these are released to the public, so you can come back and look at this. And this is actually a slide I wish I had tailored more for this presentation, but this is just to say, why are we doing this as a national lab? And some of you may already be aware of this. The National Strategy on Microelectronics Research, there's 4 goals. And those 4 goals are meant to, one, promote our domestic microelectronics capabilities, right, bring that back to the U.S. And then 2, so domestic. And 2, make us a leader in microelectronics. We are a leader, but make sure for future electronics we continue to be. And I picked the first goal that's most relevant to what I do, right? And it's so accelerating future generation microelectronics. And this was originally for some tooling presentations. So there's EDA electronics. So that's the left slide. But on the right, the key things here are non-von Neumann, new modes of computing, things in sensor computing, right? Using again new modes of computing. Edge computing, we've already talked about with Edmund, both classical computing and bio-inspired approaches. So what does that look like in the future? And also how do you combine that with more traditional microcontrollers? Like digital wireless communications is not going anywhere. We have to have some digital, and maybe in some special use cases you can do something purely bio-inspired, but we're going to have these heterogeneous systems. And then the other part is extreme environments, right? So for many of these science-driven applications, radiation hardened, high temperature, these are all real important. Now, I should tell you, if you look in the same section, they directly call out optical interconnects, low power optical interconnects. If I'd use it, not to make a pun, through the lens of optoelectronics, I would have put those in here, but it's in 1.3. So goal 1, section 3, some very relevant things and drives our motivation of microelectronics at ORNL. So I'll go over this one quickly. So I'm in the sensor electronics group. This slide, we have a broad range of applications that applies to microelectronics. I'm on this peripheral here, custom electronics, low power, analog and digital. I'm an embedded systems guy, and then I'll talk a little more about Rad-Hard. But within our group, we cover a large range of applications, right? All of them have some Rad-Hard, high efficiency, high voltage power supplies with DT generators, printed sensors, printed electronics, power systems things, autonomous, water controls, big variety of capabilities just in the sensor electronics group, and I'll talk some more about some other groups at ORNL later. Okay, so I always have to put this slide, what do we mean by low power, right? So for many people, 10 watts is pretty good, like that's gonna be in a vehicle. You're comparing that against like a server, hundreds of watts, like that's pretty good. This is a Spectrum, your mobile phone, 1 watt, depending on what it's doing, maybe hundreds of milliwatts. We're in between maybe mobile and sensor, right? So, and the goal for sensors may be sub-milliwatt, right? That in some special cases we can achieve that, but imagine if millions of sensors, the total power consumption is going to become unmanageable as we add more. So, over here, right? So just put that in some context. This is just an interesting, right? So now the best way I know to describe this is just show you some relevant projects I think you may find interesting how they relate to AI and national security. This in particular is actually where you have the sensor data is inherently analog, right? There's something called analog data deluge, right? Where we have to we're dropping information on the floor, we can't digitize it fast enough. It's not scalable. But this is some analog signal processing custom ASICs. It is a national security application, but it's looking some particular frequency signatures, some power numbers. We can talk more about that. But what I want to show with this is actually, one takeaway I want you to have from this presentation is we build deployable systems, and they're more than demonstration, they're deployable. Put them in the field and try to show that this technology is viable. And it's particularly important on applications where you need high reliability or security. We really need to demonstrate and build some trust from industry or whoever that these things actually will work. I get that question a lot. You have first principles. Why can't we use traditional algorithms where we have some guarantees? Is AI really going to be reliable here? And I truly think it is. The key is we build systems and deploy them in the field. And this one in particular is analog signal processing, but it has a digital component. It's really an autonomous system, right? But the next generation of these are going to be AI enabled, right? So this is more of an expert system. My work is how do we integrate AI enabled into things like this? Reducing power right at the sensor, analog computing, new modes, however we do that. Cool system. Okay, so here's some of my favorite, some application areas. I'm just going to briefly, I do a lot of nuclear security applications. So this is an interesting one, distributed hold-up monitoring, hold-up processing nuclear materials. It builds up in places, and a big fear of nuclear engineers is that going critical. So we have to monitor that. It's all over the duct work. It's all over the facility. So continuous monitoring, low cost systems that can be easily deployed. This one's interesting. Custom detector, SIPM-based detector. Real low power. It's an edge device. It's power from facilities. We get descriptions of things they want. Power over Ethernet. Some of them actually forbid power over Ethernet or wireless. So it's fully battery powered. Solar can charge from solar cells. It has, and I think I knew the next slide, but this has more computing. Even microcontrollers now are incredibly heterogeneous. Like what I see in HPC, we now see even in TinyML. There's multiple DSPs. There's an MPU on there. I'm not using it currently, but it's there because I want to use it. Right? So it's a pretty cool system. This is the latest. That one's being manufactured right now. So all I have is 3 model for you. Similar. Okay, so this is a similar system, kind of called Sister Project, and this is a neuromorphic computing research project that's kind of complementary to the second generation neural networks, which Edmund talked about pruning, and it's another approach. And we have a lot. I'm not a neuromorph expert, but I've been involved in enough. I could probably talk intelligent about. But we have algorithms experts like at Edmund. This one's Katie Schumann at UT, and we work together to actually build and demonstrate these technologies. And this one's really interesting. Radio detection is really interesting. It's a low SNR problem. There are really good algorithms at high energy costs. And these need to be out in remote locations and stay running for a long time. So it's a cool system. Okay, and so this is, I'll go this. So this is the required slide. What is neuromorphic computing? And I'm just going to, here's a video actually. So this is, one thing is usually these are smaller than traditional artificial neural networks. So they're just inherently smaller, right? Another thing is they're event driven. See, these are spikes. So Edmund talked about reduced precision. There's just a bit, like in between, instead of a real value in between the connections of the network I've already said is smaller. And usually we can design these accelerators to be proportional to the number of events. So what I try to do is reduce the events at the sensor. And thereby reduce total power. And it also has other nice properties, co-located processing and memory. Communicating with memory is a very difficult problem. And I want to stop here and say, so what we try to do is reduce data, cost data communication. There's a whole host of applications that we actually have to communicate some data. So we reduce data to the sensor, and then we need to transmit all of an impressive amount of data somewhere. And optical interconnects are probably the lowest power way we think we can do that, right? So having those two things combined in our work with APIC, while we're really excited about it, is going to open up a whole new host of applications. And I think I have a good one here pretty quick. Yeah, okay, perfect. Okay, so this is actually some other, I'm involved in this maybe in like a little consulting capacity or the future versions of it. But this is at the Large Hadron Collider, right? You have these millions of pixels and petabytes of information coming. We're just dropping information on the ground. We actually can't process it fast enough. So there's a hierarchical scheme where you actually have some processing in the pixel itself or right next to the pixel, and you have a trigger system where you try to reduce the data, and then it has to go somewhere else for further processing. And that's where we need efficient communications after that, right? And optical interconnects and the work like we're doing with APIC is really relevant here. And I can even think of some very other situations that have the same hierarchical kind of design at the system level. And this is another one, Aaron and Narasimha, Architecture and Performance Group at RNL. This is also one that's extremely low latency right at the pixel, because you have to process it. It comes in, you can't save it, can't really send it anywhere. right, unless you reduce it. So you have to have really low latency. And that's another approach, I didn't mention it, but that's another benefit of neuromorphic computing, just how it's structured. Okay, so I want to transition here. So another special, this isn't my specialty, but I'm on these projects, but Nance Erickson and Kyle Reed, good friend, are in the Sensor Electronics group, and this is largely their work. But what we want to do is, in many of the applications, notice they're nuclear applications, right? And also in national security, there's going to be similar things. How do we integrate this into our new AI-enabled devices? So all those previous devices, I picked parts that have a rad-hard variance or something, but rad-hard design is something we want to incorporate in that. And maybe there's something particularly unique about AI that is inherently rad-hard, maybe. So this is some really, the key, actually, what I want to show you here is going back to, like, we build things and demonstrate it. This is a cook and look approach. I like that. So what's interesting about all these, first of all, they're a novel academic, or this is a gallium nitride process, and we actually radiate it and watch. Hopefully the devices survive. Sometimes they don't, but we watch them and observe them in the process of actually being irradiated. And in this case, they're not space applications, but reactor, right, which is at much higher radiation levels, still applicable to space. So here's several systems built and tested, radiated, cooked. This is a GaN approach, and the reactor radiations. Yet another, I think I did the wireless part of this. So another interesting tie into the optoelectronics is, those are inherently rad-hard communication links, right? We're trying to do it wirelessly here, but another application is actually have optical connects outside of these high radiation environments, where we want as many sensors as we can deploy. Okay, yeah. So all right. So this is my last slide on. So we just began through. These guys have been working on it for a while, but I just joined 3 weeks ago. We had a kickoff meeting, so that's why I have one slide. All right. So and we're really excited about this. I've tried to draw some connections to how we think optoelectronics is really going to extend our current work. Heterogeneously integrated photonics and electronics. Just kicked off 3 weeks ago. This is a collaboration of AFRL, APIC, and ORNL. One thing that's interesting for this audience is it integrates AFRL T-Core secure processor. And I think Bob has some slides on that, but that's actually, I think, part of my work on this project is the integration of the electronics and with T-Core. Pretty good with microprocessors. And ORNL's focus is the electronics of the optoelectronics and packaging. And this is for this current project, we're targeting 25 gigabits per second minimum. Now keep in mind, like, this is going to be on chip. There's a bunch of those, right? So, and also that's just the first per wavelength. It has wavelength multiplexing. So keep that in mind. There's higher speed transceivers, but that's just the current target for the first year, right? And then, the target process, AIM Photonics, 28 nanometer TSMC. We use that elsewhere for other projects, some of those ones you saw previously. But we also need to consider global foundries. They have trusted foundries, trusted multi-project wafer runs, and also they have a new integrated, I'm not familiar with it, but they do have some integrated photonics processes. So we need to consider that well, particularly for the trusted foundry. But like I said, that's the first target. So to date, just got up to speed initial work. There's some work on the diode preamp and modulator drivers, some of the electronics, and we're just doing initial topology exploration via simulations. So just got started on that. I think that's it. Maybe we'll do questions at the end, right, Raj?
At the end.
So I'll do questions at the end. Happy to, but I think I'll hand it off to, I'll let Raj maybe introduce Bob.
Right.
All right. Thanks, guys.
Thanks, Brett.
Yep.
So that was a great positioning of this relationship and partnership of the world's probably one of the most best organizations as a national lab, and how this partnership evolved. I'll tell you a little later. But what I want to go back to is how we got going. My colleague over here, Bob Walter, retired from the U.S. Air Force. Long time back, and then joined DARPA, where he was the cruel guy that beat the crap out of us every day, because he was the program manager over there, and it was a hard time for us because we are physicists and we talk a different language, but you know what? He really loved this technology, and then a decade back he eight years back. He joined the team to simplify the physicsy language we talk to something that is more relatable to common people. With that, Colonel, go right ahead, Lieutenant Colonel.
Thank you, Raj. And thank you, everyone, for coming this morning. As Raj mentioned, my primary job at APIC is to translate complex particle physics into standard language that everyone can pretty much grok, understand. How many PhDs out there? Okay, those of you who didn't raise your hands, you're my people, okay? So we have a problem, a huge problem, and that is, the emergence of AI and hyperscale data centers are growing beyond our ability to produce electrical power. This chart on the right side there shows one of the many projections of the increase in power consumption. And every different source you go to has got a different projection, but stands to reason, it's huge. And I'll take a note from a buddy I talked to last night, Joe Consolini. He said, look, people don't really grok terawatt hours and so forth. So if you can kind of convert that into something people can relate to. So 1 terawatt hour basically can power 100,000 homes for a year. So, when we're projecting up here up to 1,000 terawatt hours, that's a huge increase in electrical power consumption. The root of the problem, kind of get down on the micro scale here, the root of the problem is on your basic circuitry on the motherboard, okay? Everything communicates on the motherboard over copper traces. And as we continue to shrink the feature size down of these various processors, we need to have more and more bandwidth and shrink down the pitch count for the connectors into the processors. And we've reached a point where we just can't keep scaling down those connectors. And as you try to compensate by pumping higher data rates over copper, copper becomes more of a resistor than a conductor at higher frequencies. And so a lot of the power that is being consumed in these data centers, and especially some of this NVIDIA Blackwell AI processor, is in the copper interconnects. I mean, I was really kind of surprised to learn that the NVIDIA link and their NVIDIA switches, it's all copper-based. So the idea is, on a macro scale, we take fiber optics, right? It's used in telecommunications, extremely high bandwidth, extremely low energy consumption, and it's dynamic network. And we shrink that down into that chip scale, so now we can communicate between the processors and memory and other chips on and off the board over an optical network, over fiber, as opposed to copper. So to give you an idea of what we've been able to achieve at APIC, this was a study that was done over 10 years ago, commissioned by National Security Agency, conducted by Department of Energy with a host of academics involved in this. And they said, look, we're coming to the end of Moore's Law. What are we going to do? What technologies can we incorporate to kind of keep the essence of Moore's Law going? Photonics is one of the areas they looked at to be able to continue to shrink feature size and be able to provide the necessary bandwidth. So what this graph represents here, the vertical scale is energy consumed. The horizontal scale is sort of where you are on a chip in a processor. That vertical blue line in the middle of the graph represents on chip to the left and then going off chip to the right. And you notice there's a huge increase in energy consumed when you go off chip. Even with an active optical cable connection, that's only for the motherboard, you still got to traverse about 7 to 10 centimeters to get to the AOC connection. So it's roughly 2 orders of magnitude more energy consumed. So back then, they projected that, look, to make photonics really feasible, you have to get the energy consumption down to 1 picojoule per bit. We took our technology that we had developed originally for other purposes, and in consultation with the National Security Agency and others, we developed these photonic links and architectures, and we can get our link down to 0.1 picojoules per bit. So not only do we meet the mark, but we exceeded it by a factor of 50. Not too long ago, this same group of people, mostly the same group of people, redid their study and looked at, hey, where have we come since the original PEAT study was done? And the bottom line for repeat, it was called, is that photonics really hasn't advanced because the cost, I mean, it's very expensive. Well, I won't get into it. But, and also the packaging is very complex, advanced packaging, which fortunately now we have Oak Ridge National Labs working with us to help us overcome that obstacle. So here's our, in the grand scale of things, this is our approach. We've solved the physical layer issue, replacing copper traces and circuit boards with this transparent fiber network, okay? But I look at that, it's like hooking up a fire hose to the spigot on the back of a house. You gotta adjust that spigot so that it can fill up that fire hose. So that's what the Photonic I/O is about, is developing the necessary protocols and interfaces to the processor and memory to take advantage of that huge bandwidth that's now available by means of photonics. And then the third pillar is the global coherent memory. So imagine we take this optical network, dynamic mesh network, and we can connect every memory chip, every piece of DRAM in this, not only just that motherboard, but the entire server, the entire rack, and across the whole data center, all stitched together to form a global coherent block of memory that each and every processor or GPU or whatever, FPGA, can connect to and read and write. Huge advantage for, big data sets, large models and simulation. Certainly lends itself very well to artificial intelligence and neuromorphic processing. And we coined that network cache coherent distributed shared memory. And we've modeled this stuff. We've shown through our studies with NSA that we can scale this up to a supercomputer size system. So our vision, our objective at this point for high performance computing and AI is to be able to reduce the energy consumed in these systems by a factor of 23 times. So that's not 23%, that's 23 times. That's like 95%. And we can also make the systems much smaller, 40 times smaller. But look, data centers and AIs, we're not really real estate constrained. So for that aspect, it's not as important. And fortunately, right now, we're working with, like I said, Oak Ridge National Labs is helping us with the packaging piece, being able to stitch this stuff together. And we're also, interestingly, working with the Air Force Research Lab. They're not only our contracting agent, but they're also our partner, and they're contributing the first processor that we're going to use to integrate with photonics, and that's the T-Core processor, which is like I think I have a slide that addresses that, but it's like the TPM chip on your laptop or processor on steroids. It is a quantum proof. It incorporates quantum proof cryptography, and it's really hugely important for all things DoD, and there's some commercial applications as well. I think I have a slide that addresses that. So here's the impact, going back to the macro scale here. On the right side is the projection I showed you at the beginning of the brief. With our timeline for development, manufacturing, and so forth, we can bend the curve. We can dramatically reduce the energy consumed by AI and data centers back to even below what they currently are. Think about the huge cost savings. You know, right now, they looked at this chart on the right, I'm sorry, on the left there, and they said, oh my goodness, a huge amount of energy required, what do we do? And of course, everyone's talking about nuclear power, bring more power plants online. This stuff takes, 7 to 10 years to get online, and at huge cost. And that cost, who's going to pay for that? It's all going to get passed on to the taxpayers and the consumers. Short story, we went to Google several years ago and said, hey, we got this new technology. We can rebuild your data centers and cut your energy consumption by, a factor of whatever. And the CEO says, well, what do I care about that? That's going to cut my revenue. We just pass those costs on to the customer. If I incorporate this, you're going to reduce my revenue, and it's going to look bad to the shareholders. So it's that kind of think that we have to counter with this new technology. And of course, there's other attributes as well. This is T-Core. Again, this is a quantum-proof encryption, cybersecurity, hardwired. It's not something that's going to be overtaken, in a few months like some of our antivirus software. This has been worked on, developed by the Air Force Research Lab over a period of more than a decade. And this is the future for securing our weapon systems and anything. I mean, think about this. We're talking about having these autonomous systems out there, autonomous aircraft, fighters, sensors, and so forth. Do you really trust that thing to be out there in the environment where they can be attacked, through means of cyber attack? And what happens if that autonomous system gets compromised? So we have to have a means to secure these things and make sure they perform as functioned as required. Quickly, this is sort of our roadmap for the first prototype we're going to build. The end systems we're looking for is for DoD applications. And it's important that we get more computational power out at the edge of the spear so that we can sense data, sense intel, bring it in, process it there on site, and get it to the war fighter as soon as possible. I do have a short vignette that, back during the height of Afghanistan war, they used to collect huge amounts of data with some of the new sensors that they had out there. And literally they would collect petabytes of data. They didn't have the capability in theater to be able to process that data. They used to try to do change detection, try to figure out where these IEDs were being planted in the middle of the night by looking at what soil has been disturbed along the various routes of the units. It sounds crazy, but what they had to do is take those petabits of data that they collected when the aircraft landed, put it in a C-141 or a C-17, fly it back to the United States, 12 hours later, put it into a data center that could process the data and do the exploitation, and then send the results back out to the warfighter. We can't afford to do that. We have to do the processing at the edge. This is our bigger roadmap for high-performance computing and AI. As I said, we start out at the bottom there with our first-generation multi-chip module, which is designed for embedded processors for weapon systems and just various applications. But then we slowly build up and become greater sophistication in our system until we can achieve the objective of a exascale computer. Okay. That concludes my portion. I'm going to turn it over to Raj, our CEO, founder, visionary for this technology. Yeah. And he's also going to talk about some of the other applications of the photonics beyond just high-performance computing. Thank you.
Thank you, Bob. Brett, did I hear you say the Hadron Super Collider?
Yeah, so I gave the application where they had that large pixelated detector, megapixel, right?
Yeah.
And if you, we talk petabytes, it's petabytes per second.
Yeah.
Impressive amount of data, right? Yeah, so that was one application I thought.
So I just need to, it brings back some beautiful memories. I happen to have been born in one of the poorest cities in the world called Calcutta, India. And I was really blessed that my uncle was Satyan Bose, who, with Albert Einstein, wrote the general theory, the special theory of relativity, and the Hadron Super Collider. His first Nobel Prize win was the Higgs boson. I'm sure you guys all remember that. So it brings back good memories, my friend. It's a brutal childhood studying under someone like that. I then graduated. I went to Indian Institute of Technology, got my BTech honors, and I came to the US to do what I do for a living today. I did my grad school and pursued this dream. So let's talk about if you do these technologies, what is it that the US government told us to focus on in terms of vertical applications? So obviously the low-hanging fruit in this is the high-performance computers. Why? Because once NSA got involved with what we were doing at DARPA for the Joint Strike Fighter, one of the critical things that NSA said is, hey, we have supercomputers. And you may or may not know, one of the foremost supercomputers in the world was built by a guy called Seymour Cray, called the Cray computer. There's generations of that, and it was all funded through NSA. And so they were looking for the next generation, as Bob just said. You're not going to take a machine like that with all this overhead and immerse it in liquid nitrogen, which is how they got their speed advantages. So they were looking for something new and novel. And the main push from NSA was, we are really not into buying the links, as I stated in the beginning of my presentations. We're not looking for the laser and the modulator and the detector that you do for the Joint Strike Fighter. What we're really looking for is a system. So that resulted in us embarking on this journey of defining a system. Separately, there was a competitive win for us on an organization called IARPA. So you talk about DARPA, and then IARPA is intelligence ARPA. So under that auspicious, we designed and built this, defined the system that we are now embarked on to build the first prototypes. And what it showed was, we have this massive reduction in power. First generation is factor of 23 in size, which is what they wanted for the supercomputer. So that's one. The commercial application, even in the defense market, is a small market. As Pricewaterhouse has been doing the studies for us, is to the tune of about 120 billion a year. So that's a significant number. The other verticals are, and I'll show you something that we have done on quantum. Then specific space application, the government made it very clear to us. Hypersonics. And then, of course, what we are here for is AI and autonomous applications. So with that, let me embark on the quantum. So one of the devices that we did, which was the detector for the Joint Strike Fighter, it had to be super linear. It took us a long, long time to finally achieve that detection ability. And National Institute of Standards had bought a handful of them a few years back. And I was pleasantly surprised when one of the postdocs that we funded several of the major universities, MIT, Stanford, and all that. So one of the students that financed her postdoc called me. She's from the University of Alabama. She said, hey, I just saw this publication by NIST on the value proposition of doing photonics for quantum design. And they said the devices that they used happened to have come from APIC. I said, well, that's interesting. So I called up NEST, and they said, yeah, it's the only ones that work at 22 millikelvin. All right, and as you well all know, that at 10 degrees Kelvin, the electrons are freezing. So question was, we did achieve that. And I now understand why we did, but that's a separate topic. Also, how HIPPE and T-Core can be used for space. And the main thing over here is to appreciate that for space, if you use photonics interconnects, you get rid of electronics. So when you get rid of that, the less you have, less hardening you have to do is also shielding. So you reduce the weight requirements, and for space, every ounce is important in terms of launch. And then, of course, we reduce the power consumptions by a significant amount. So, this journey to Mars will last a little longer. Good thinking, Elon, but hopefully you'll come and talk to me soon. So I'm just joking. Also, the T-Core provides the security. This is extremely important. So, this little jest at the bottom of HAL 5000. Hey, you have no choice, my friend. You better come and talk to us. Hypersonics, similar issue. That's in space, and you're going to reduce the weight using this technology. The optical interaction. So just keep in mind, we are not chasing the CPU or the GPU or the memory. What we focused on is the reduction of energy instead of on copper along the printed circuit board. We use a multi-chip module using optics and photonics, and that's what we have done. All right? And that's where we are getting the significant amount of power. I'm really focused on doing this technology at 28 nanometers. And we've gone through a lot of thinking with several of our partners. At 28 nanometers, 28, 22, we're home free. And when you see my next one or two slides, you'll see why, in order for this nation to move forward quickly, we need to transition into production at 28 nanometers. And I think the big guys like NVIDIA, they can have their GPUs suck up all the energy and do the great AI things that they're doing. But I think we have sufficient ammunition to move forward at 28 nanometers. The same applies for autonomous systems and AI. We are all looking at the massive demand in AI. I mean, every time I turn around, all these celebrities who talk, Sam Altman and this guy who wants to go to the Mars, and he's bringing Tesla and all these things. They say, man, we need AI. Well, the problem is, how are you going to solve the energy problem? The demand on the energy of these systems is massive. And okay, we'll let you build what we are hearing. We'll let you build the power stations next to these data centers. Great. I still need to bring in that power. Well, here's what we have done. Drop the power using, this beautiful technology that we have been working for decades and have now solved. So I want to make sure you appreciate that point. Let me drive you to another new hot subject, which is called the Golden Shield. When I started my career in the government technology business, I happened to be working for a company that was part of the defense transition team for President Ronnie Reagan. And he stated something. He said, I want to create Star Wars. So, a bunch of us scientists said, all right, the president wants it, we better figure it out. So we launched into Star Wars, and the only nation has really implemented it well are the Israelis. And it's nice to know that, it's back in again, because those days our motive was doing technology in the Defense Department was worth it because it was peace through strength. We avoided going to war because we as Americans are the greatest nation in the world. And our technical success is what makes and keeps peace in this world. So that's why I think what we have now laid out as a roadmap using the T-Core processor for protecting, for doing the Golden Dome that we are recently hearing about, and our technology really has a major play in that. Now, I want to take the next couple of minutes before we end this conversation that when you chase these technologies, as scientists, we tend to focus on a very important niche, which is, okay, for us was drop the power. But here's the problem. Reducing the power of these systems and servers, I think we are solidly on our way to do it with what we are doing with Oak Ridge and the Air Force, and we'll have that as products. But let's talk about the chips. The whole world of the chip industry is chasing 5 nanometer, 3 nanometer, 2, and very soon it's going to be 1 or below. Well, lithography that makes those chips are photolithography run by an organization called ASML. When we built our first photonic fab, we were the first company 20 years back, 25 years back, built the first photonic fab under DARPA funding and government funding. I didn't have the money to buy a lithography machine, so I went and convinced ASML in Veldhoven. I went and talked to the technical guys, and we're still friends, and they gave me a lithography machine. And out of that came many patents, and we realized that lithography is extremely important, and today the Dutch and ASML literally control the entire market of lithography, photolithography. And there are major political issues going on between whether the Chinese should have it, who should have it, who shouldn't have it. So if you look at the 2 nanometer ASML lithography machines, just the top end machine takes 34 gigawatts, and you need about 30 of these machines to run a production fab for chips. Well, you're, as we say, SOL, because you may have solved the system server problem, but if you now, in order to build the chips that build the servers, takes so much power, how do you solve that problem? Well, we've been quietly working away at it, and I think we have figured out how to do that using our HIP technology and multi-electron beam. I wanted to make sure that as technical guys that we look at the full big problem and solve every aspect of it. And so we haven't embarked in a complete way to implement this, but we have done enough work to convince ourselves that we are solidly in path. Given that there's very little time left, what I would suggest is all of us are available to talk even if we switch this off and continue to answer questions face to face, if that's okay by everyone. Is that cool? Thank you for your indulgence. I really appreciate it.